Okay. So for 3.2, we're going to be talking about exponential and logistic modeling. And so, as I mentioned before, exponential functions and logistical functions are great functions that we could use in real-world modeling, especially biological and ecological types of studies. If we want to predict the populations of a certain type of species in an environment, that's what we would use this for. And so usually the functions represent growth or decay rates of certain populations. And so, for example, number 1 in your textbook, and I'm not going to write every word down. Well, we could just read it from the textbook, I suppose. Example number 1 from the textbook says, determine the population, tell whether the population model is an exponential growth function or an exponential decay, and find the constant percentage rate of growth or decay. And so they give us 2 examples, and those I will write down. So for the city of San Jose, we have that the population growth or decay starts off with 782,248. Let me get that on the screen so you could see it. Times 1.0, and I'm gonna chop this off a little bit. 1 raised to the t. Now remember, for an exponential function, that usually looks like y equals a times b raised to the t. We said that b was normally what we would call the base. That's the thing that we multiply by itself, t times. A, can anybody in here tell me what a is? Who remembers? It was right before we went on the 3-day break or whatever. It's a constant, right? Which is a constant, it's a coefficient or a constant multiplier, but it's usually a number. It doesn't have a variable, usually, although it could, I suppose. But it was also the initial condition, right? That's what we found. Yeah? Okay. So, and in most cases, it is what we call, it's the y-intercept, because it occurs when t equals 0, right? And when t equals 0, and normally when we plug this in the calculator, we would say x equals 0, right? So it doesn't have to be t, it could be x. But when we graph it, usually it's the y-intercept, which is the initial condition in most cases. Now, when we're talking about growth and percentages, we rewrite it a little different. We say that the function of a population is equal to p naught, or p sub 0, times 1 plus the percentage rate raised to the t. So all this stuff that I've written down applies to this. The only thing that changes, what we used to call a base is now 1 plus the rate, which is like the percentage. Okay? So if we come back here, and I've abbreviated it because I ran out of paper space, what is the percentage, and is it a growth or is it a decay? Well, what we could do is let's rewrite that. But let's try to take this and rewrite it as this particular equation. So I know what my initial condition is. My initial population, p sub 0, is 782,248. 782,248. But now, how would I write 1.01? Like this. I could say 1 plus what? And if you guys aren't quite sure what Mr. Adams is asking you, I want to take this number but represent it this way. Could I do this? Would that work? Yeah. So if this is the percentage as a decimal, what would that be as a percent? Well, 0.01 is the rate. It is a positive value. So that means that it is a growth. In other words, over time, this number keeps growing and getting bigger and bigger by 0.01. So, as a percentage, though, it's really 1%. Does anybody have any questions about that? So that's a growth. Now, what else did I say we could use this for? Decay. So now, the Detroit one, let's see, I'm going to write Detroit's down. They have a model for Detroit. And the model for Detroit is this. The model for Detroit is that the population as a function of time is equal to 1,203,368 times 0.9858 raised to the t. So anyways, we know that this is the initial condition. So whenever they started this model, this is what the population was when they started the model, when t equals 0. And I suppose if we read, although the textbook doesn't really give us the answer, who knows what year it was. But one year they said, hey, let's try to model the growth. And at that year, they had 1,203,368 people. And then they measured how many people they had a year after that. And then they measured how many people they had after that. And this is the mathematical model they came up with. But what the textbook is asking us is, what is the percentage of growth or decay? And we're going to get that information from that part that I circled there in orange. So what I want to do is I want to write this to look like this, where I have the initial population times 1 plus the rate of change raised to the t. So if I rewrite my equation, my population as a function of time would be 1,203,368, right? And then over here, I'm going to say 1 plus or minus a number raised to the t. Well, the only way I could get 0.9858 from 1 is I have to subtract something from 1, right? If I add a number, it'll be greater than 1, and this number is clearly less than 1. So how do I find the difference? Well, what I'm going to do is I'm going to say 1 minus 0.9858. That's my growth or decay. I'm trying to be ambiguous as possible to make you guys think about this, but I'm kind of also giving the answer away. All right, so if I'm subtracting, right, if my R has a negative value, what would you call this, a growth or a decay? It's a decay. Now, it's still a percentage. What they're doing is they're losing 1.4. So what this means in regular plain English, if I were to describe this to somebody, you know, what's going on in the city of Detroit, they're losing 1.42% of their population every year. So probably when we had some problems in the auto industry, people who used to work in Detroit for the auto industry had to find jobs other places, so they moved out of town. And at this particular point in time, when they started to conduct the survey and make this population model, this is what was going on. So they had a decay in population. Does that make sense? Does anybody have any questions on that?